Okay, I think we'll get started. So thanks everyone for joining. Just a little bit of housekeeping before we start proper. Um, so yeah, we'll be recording this, so just keep note of this, and we'll have this on YouTube probably later this week. We can send a link for that if you need. That'll be sent through to everyone who registered. Keep your microphone and camera off, and that just means we can focus in on the presenter and what they're sharing. In terms of questions, we usually leave that till the end. So please just add them throughout the chat, throughout the presentation. Brilliant. Okay, so yeah, let me just introduce myself. I'm Stephen Haben. I'm a data science consultant at the Energy Systems Catapult. And thanks for joining us. This series of seminars is really to sort of try and share more widely what's happening in digital and data in the energy sector. And so we're very pleased today to be introducing Dr. Alessandra Parisio, who's from the University of Manchester. I'll do a little introduction and then she'll give a presentation and then we'll have a few questions at the end. So Alessandra is a reader in the Department of Electrical and Electronic Engineering at the University of Manchester, where she researches projects in the areas of building energy management and distributed control for flexibility services and grid support provision. The project that she's won over the last few years has totaled in about £7 million for the University of Manchester, and her main research interests include the areas of energy management systems under uncertainty, model predictive control, and distributed optimization for power systems. So I'll stop sharing now. So if you want to share, Alessandra, I'm very happy to introduce you and looking forward to your talk.
Yes, thank you very much. I hope that you can see my slides. Okay,
Yep,
great.
see that. Thank you.
Great. Thank you very much, Steven, for the introduction and for the invitation. I'm very happy to be here. It's a pleasure, however, virtually. So in this talk, I would like to share with you some of the results we got within some of the research projects I've been involved in particular, a Horizon 2020 project, Crossbow, and two EPSRC projects. One is the SuperGen Energy Network Hub, and I will tell you a little bit more about it, and multi-energy control of cyber physical urban energy systems, which was a UK-China project just finished. So basically, most of the studies I will mention, I will briefly introduce, have been conducted within the SuperGen Energy Network Hub and within the Crossbow European project. The SuperGen Energy Network Hub started in 2018, and this has been now renewed for another 5 years. And it involves 7 universities, and the Energy System Catapult is also involved, and several relevant stakeholders like network operators, service providers, city council, and so on. And the main aim is to design and evaluate energy network solutions from different perspectives. So we will be looking at the value of the data, how to use data for several purposes, including how to use it to enhance the decision making. And then we also consider market regulatory instruments and risk and resilience, and also policy and social factors. We also will monitor the UK trajectory towards net zero transition, and also look at how to estimate future trajectories and produce a roadmap towards net zero, taking a whole system approach. So if you are interested, of course, I encourage you to visit the website of this project. Now, before outlining more technical aspects of this distributed optimization-based control frameworks, I would like just to spend a few words describing the research context and the motivation for the research. And actually, as we all know, we are witnessing a major paradigm shift in the power grid to help the future power systems to address the challenges of meeting and increasing energy demand and net zero, of course. And we are trying to address these challenges through a growing penetration of renewable energy sources, which result in new challenges to the operation stability of the power grid, in particular frequency and voltage at local level. And to mitigate these challenges, as we know, the flexibility is a key concept. Flexibility generally can be defined as the system ability to cope with events that may cause imbalances between supply and demand and at different time frames. And we now need more and more flexibility, especially in the at distribution network level. And in these slides, I just included some of the main flexibility resources that can be available in a future energy grid. So we have on the right side multi-energy systems, where they are systems where multiple energy vectors interact and have to be co-optimized and coordinated. And buildings in these scenarios can be seen as multi-energy systems. And then we have on the left side storage systems. And actually in the future, we expect thousands or even millions of storage systems, including electric vehicles, to be connected to the distribution networks by all types of consumers, and they have the enormous potential of being employed as alternative to large-scale generation storage plants to provide system-level support and also guaranteeing the local network stability. And the impact of individual device is, of course, very low, but aggregating a large number of them, of simultaneous responses from them, can have a major and significant impact. So the storage devices need to be operated and controlled as virtual storage plants. And then of course, it is very challenging to coordinate a very large number of these flexible resources, especially if the goal is to coordinate their responses and have a delivery within a required time based on the system operator's instructions. And for some of the services like fast response, the delivery must happen within 1 second. And these responses have also to dynamically adapt to a time-varying and uncertain environment. So traditional control methods now we know, we have knowledge that they are not suitable. And so this is the main motivation of our studies, to explore the potential contribution from flexibility resources, in particular now distributed energy storage technologies and buildings seen as multi-energy systems, for a more efficient energy network. And then the scalability is the main property we are interested in. So these control frameworks need to be able to optimally coordinate an arbitrary large number of flexible resources in a very short time, and accounted for both local and global objectives. So the first step is to identify the most suitable control architecture to do that. And I would just like to very briefly mention that we can see 3 main categories. So the centralized, the decentralized, and distributed ones. For the centralized, in the left side, the figure in the left side, of course, is not suitable because given the increasing number of diversified assets to control and manage, and also the current trend to reduce the time scales of the grid operation and the services, these approaches are not practical because they require high computational and communication requirements, and they have also they are highly sensitive to communication delays and single point failures. On the other hand, fully decentralized approaches like Drupal control techniques, for example, they suffer from instability and suboptimality issues because the decision making is based only on local information, and global aspects are not considered. So because of that, I mean, we will adopt distributed approaches, which basically rely on local and neighboring information and try to combine the advantages of both decentralized and centralized approaches because they are far more scalable than centralized approaches, but they can achieve a better quality solution than decentralized approaches. Furthermore, another feature that we would like to embed in our control framework is the data. So we want to leverage data for decision making because these control frameworks rely on ICT technologies, so on local communication networks, and of course on data. Data can be used for a wide variety of purposes. So data can be obtained from local sensing equipment or broadcast by system operator, or we can use historical data to make predictions and estimate model parameters. So here we can see that you can see that we are exploring the use of data for deriving control-oriented dynamic models of the system we want to control, learning automatically control inputs, obtaining automatic tuning of the cost parameters and constraints, and identifying models of the environment because our flexible devices interact with an uncertain environment, and data can help with capturing the main features of this environment. And this is what we will mainly focus on this last point in this presentation. And I also would like to mention that there are different categories of this data-driven control design, but we mainly we can generally identify, as been recently proposed in the literature, two main broad categories. So the indirect data-driven design, where data is used to perform any kind of identification. So you can identify dynamics of the environment, as I said, model parameters, predictions, elements of the control design. Direct data-driven design, where data is directly embedded into the control algorithm without any direct form of identification, and it's mainly model-free. We have also used that, but it's not the main topic of the presentation. So what I will present now is a couple of indirect data-driven control algorithms with application to virtual storage plants and multi-energy networks. However, I think I will be able to go through the first point here in the slide about coordination of storage devices for improved grid support service provision. Basically, here you can also see some of the main publications we have on the topic. The second part of the slides focus on a decentralized predictive control approach with coordination, with energy coordination for managing an arbitrary number of buildings and their host networks, considering both electrical network and district heating and cooling network. I will not be able to go through both of the the parts, but I will be happy to share all the slides after the talk. And if you are interested, please I would be happy for you to get in touch with me, of course. And I also would like to take the opportunity to thank all the researchers I've been collaborating with for this work, in particular Tian Chao, Yi Chao, Michael, that are postdoc and PhD students who mostly work on developing this framework, control frameworks, and the colleagues, Professor Milanovic and Dr. Marjanovic from the University of Manchester as well. So I will start, as I said, with distributed optimization-based control frameworks for coordinating and managing virtual storage plants. And these frameworks are based on online convex optimization. As some of you might know, or all of you might know, online convex optimization is a relatively new field in the intersection of game theory, optimization, and machine learning. It is basically an online process requiring agents to interact with the environment at each point in time. And the environment has unknown dynamics. And this framework, is very interesting. This framework is very interesting. This field is very interesting because it requires less computational power, and so it's very promising for real-time implementation. And in this framework, basically there is a player that plays a repeated game over a given horizon T, and it selects an action from a convex set of strategies, and after interacting with the environment, it suffers a loss. And of course, to account for the uncertain time-varying renewable generation and load, we did not consider, as in the traditional OCO setting, a fixed environment, but an unknown and time-varying environment. In our case, basically, the player is a battery with a time-varying objective function. These objective functions can include battery costs, reward for the service provision, also battery degradation aspects, as you see on the right side of this slide, and also tracking goals. So the decisions to be made is about how to control the active and reactive outputs from the storage devices to provide the service cost effectively, and also about the charging and discharging. And of course, the main goal of this free algorithm is to generate decisions and then optimal set points for the devices, so that a regret function is sublinear and converges to the sequence of best dynamic decisions. And this regret function is basically the difference between the obtained decisions and the optimal solutions, so the best dynamic decisions. Now, this framework, the algorithm, the OCO algorithm, has to be designed so that these performance metrics are sublinear. Being sublinear, it means that you have an improvement over time. And these main important performance metrics are the dynamic regret, which quantifies how well the player learns over time, and the dynamic fit, which quantifies the constraints violations. So I would just like to mention that we included battery degradation aspects, for example, limiting the number of cycles of charging and discharging, or putting a cost on the power exchanged with the batteries, but I will not go into detail. Now, for the fast frequency support, the first step is to formulate the optimization problem, which has to be solved in a distributed manner. the problem for fast frequency regulation, fast frequency support, is formulated in this way. We want basically the storage systems to change their power output proportionally to any frequency deviation, while minimizing the storage related costs, which include degradation, the efficiency, and the reward for the service provision. And we included relevant constraints like the frequency dynamics, the storage dynamics, and its relevant capacity and operational constraints, the delivery of the contracted power, which is basically the coupling constraint. And we also included a constraint that limit the ramp rate to be proportional to the rate of change of frequency. This is done to avoid stability problems caused by sudden and quick storage responses. And through tuning the alpha and beta parameters, you can also tune the ramp rate response according to performance requirements. And then I would here just like to briefly outline how the algorithm work, what are the main steps of the algorithm. So it's basically, usually OCO algorithms are based on a primal dual approach combined with consensus for a fully distributed implementation. And you can see here the problem can be rewritten in this compact form where we have local sets, so agent level sets. So we have, for example, here a network, a power network with 5 battery systems, each equipped with a local controller, which will perform the steps of the algorithm. And we have, of course, local constraint, but we have also a supply-demand balance constraint, which is global. And it's the coupling constraints. And that is the problem when we want to allocate a computational burden to the different agents. And then the steps of the algorithm are these ones. So we start with an initialization phase where there are local parameters that are initialized by each of the agents. Then we have a consensus-based local estimation of the supply-demand balance or mismatch, which is basically the coupling, the global information. But since there is not any central entity, each agent has to perform a local estimate of this global information, and the information coming from the neighboring agents, here, for example, each agent has 2 neighboring agents, can help over time to improve the estimation of this global information. And basically, so this local information is also based on local measurements, local information about renewable generation, load demand, and frequency. And here, the batteries actually need to know in advance what is the contracted power they have to provide. In the next framework that I'm going to present, we also will drop this limitation. So the next step is involves some local updates of the control inputs and the duals, and then the power set points for each of the agents are calculated and actuated by the local controllers, and these steps are repeated at each point in time. And the regret function, so which I said is one of the most important performance criteria, is proved to be sublinear, so to convert to the best decisions asymptotically. And then I will just give a few simulation results. So here, for example, we discussed the plug-and-play capabilities of a distributed control framework. We consider an IEEE 33 bus system. It's a radial distribution system where there are 10 batteries with different power ratings connected at initial time t equal to 0, the system is exposed to an unexpected and sustained supply-demand mismatch. And an increase in the load, basically. And one of the storage systems, as you can see from the right figure, fails to operate at this time, 4 seconds, during the frequency drop, and actually it is recovered after some seconds, so at 23 seconds. But in the left figure, we can see that the system frequency is regulated to the nominal value within the expected time. Irrespective of the storage failure. And this is one of the advantages of distributed control frameworks. And then here we have the regret function. So we see that after a few seconds, the players, the agents, the batteries can converge to the sequence of the optimal decisions. And in this table, we show the scalability of the algorithm. So with an increasing number of agents, even up to 2,000 battery systems, the proposed distributed algorithm can calculate the power set points within half a second, whilst centralized approaches would not meet the response time requirement of the fast frequency support service, because they take over 2 seconds. Then here we consider the automatic generation control. So we consider a slower frequency support service. And this is a contribution that we are interested to understand the contribution that can come from coordinated storage devices to this type of, because this is also a very important frequency balancing mechanisms that has been traditionally, of course, provided. So this is AGC operates in tenths of seconds, so it's slower, and is done in response to net load variability to maintain the scheduled system frequency and also the timeline power flow. So that timelines that interconnect different control areas. And basically, this mechanism is based on area control error, which is basically an error signal for the area imbalance that uses a static frequency bias. But in practice, of course, there is an uncertainty here, so there is a discrepancy between the frequency deviation, the frequency bias, and the actual area's frequency response. And also, with the growing use of variable renewable sources, the regulation burden has become more and more challenging, because actually synchronous traditional generators that traditionally provide this type of service are not able to respond to the quicker, faster power imbalances due to their ramping rate, the large inertia. So the system operators are exploring the contribution that can come from fast controllable devices like power electronic-based battery systems, because they are able to ramp up to full capacity within 10 or 100 milliseconds. So batteries can also provide symmetric support in both directions, because we can have power shortage, but also excess power. And they can switch direction instantaneously. So they are very promising. So there are many utility scale battery projects with AGC functions that have been commissioned worldwide. However, it has been observed that batteries do not always contribute efficiently to the minimization of these area frequency deviations. And they can even cause counterproductive regulations. This is due because of the neutrality needs of energy storage, because actually this can require a portion of the batteries involved in the service provision to act in the opposite direction to prevent overcharging or over discharging. And also batteries can overly correct the error due to a lack of coordination between them, among them. And this overcompensation has created regulation requirements in the opposite direction of the area imbalance. And this can lead, as been observed, that this leads to sustained oscillations in the frequency system, overall system frequency. So there is a need to properly coordinate the batteries and also account for their limited capacity. First of all, we modified the signal to be broadcast to the batteries. So it's we are not using the area control error, but we we propose a modified signal to steer the batteries. And then we design a distributed online convex optimization-based algorithm to coordinate the batteries based on this modified signal. So the problem is that the area control error relies on a static bias setting and do not consider the nonlinearities in the turbine governors of the synchronous generators, and also do not consider the uncertainty coming also from the load side. So to account for the nonlinearities in the turbine governors of the synchronous generators, the concept of area injection error here has been recently proposed, which uses basically direct measurements of the generators' power injections. However, this is based on a quasi steady state approximation, and it is subject to the slow turbine governor dynamics of the generators. And this resulted in a slower convergence than the area control error. And additionally, bias uncertainty on the load side, as I mentioned, has not been considered. So to address this challenge, we first modify the area injection error, removing the quasi-steady state approximation and introducing a feedback loop to account for the transient of the generation side, which implicitly leads to a dynamic bias setting. And also we included an additional term here to account for the load uncertainty due to the increasing number and diverse composition of other frequency responsive resources, such as wind turbines, electric vehicles, demand-side technologies, and which will be more and more available in our power grids. But because of the complexity, we resorted to machine learning and data to estimate and emulate the response at an aggregated level, because we are at the transmission level now. And we use an online interpolated radial basis function network to produce a local approximation of the aggregated power frequency characteristics of these frequency responsive resources, which is based on data that are dynamically collected by each bus agent, area frequency measurements and power changes. And we incorporated it into the modified area injection error signal. And we also use adaptive learning rate to account for the changing nature of the system. So this system, this signal, this area injection error signal, can be interpreted as the ramping reserve that needs to be allocated to the various battery agents, based, of course, on their current capabilities and capacities. And this is the formulated problem, which also accounts for the charging-discharging modes of the batteries. And this algorithm is solved with is based on online convex optimization with online learning, and basically the batteries can act as a complement to the generators to satisfy faster area ramping needs and suppress the net load variation, resulting to an improvement of the system's transient performance. And basically, at each iteration, each battery has to first interact with the environment, implement the control action, and after that, the actual cost can be calculated and the loss, the regret can be estimated. And all the data, the observations at each iteration, T, will be utilized to correct the previous decisions at the next iteration, next point in time. And this is a mechanism that improves the decision making over time towards the optimal decisions. And we also proved under mild conditions that the algorithm provides guarantees for sublinear dynamic regret and dynamic fit without the need of using future predictions or global information. And I would like to stress again that the sublinear properties is required to make sure to guarantee that there is an improvement over time. And then for this case study, we considered an IEEE bus system, and data are also gathered online and corrupted by adding a small Gaussian noise. For this first simple case study, we consider 5 batteries connected in the area, in the first area 1 here. And we consider a step load increase of 5 megawatt occurring at 10 seconds, after 10 seconds. Now the frequency responses of the 2 areas are shown here in this figure to the top right, and the red areas here represent the improvements in the frequency profiles that are due to the coordinated action of the responses from the batteries. The green areas show the effect of incorporating the load uncertainty through the radial basis function network in the area injection error signal. And here in the bottom left in this figure, we introduce step changes, repeated successive step changes as represented in the green line here. And with positive values indicating power deficiency and negative value excess power. And as a result, the batteries shift between discharging mode and charging mode to counteract the area injection error. And here we can observe a high degree of synergy between the batteries, the blue line, the battery response is the blue line, and the responses from the synchronous generator, this pink line, because they actually complement each other when compensated for the imbalances. And here we can also see the dynamic fit per iteration, and the dynamic fit measure the non-compliance with the ramping needs, so the violations that are still not compensated. And we see that after a few seconds, it converges to 0, which means that there are not imbalances. And also the cost, here the dynamic regret converges after some seconds to the optimal one. The optimal one is the one for this centralized problem that have access to all the global information. And sorry, this additional case study wants to test the scalability of the algorithm of the control framework, and also the sensitivity to different network communication network topology. So we here consider a two-area IEEE 39 bus system, and that the communication network topology is shown here. So we have a linear topology in the area 1 with 6 batteries, and a mesh topology in the area 2 with the remaining 33 batteries. And here we also see again net load variations introduced in the area 2, and which are represented by this green line, and we can see the dynamic fit, which represent the imbalances, this blue line. We can see that the imbalances are kept very close to zero all the time. And here we can also see that the computational times for coordinating six batteries in the area 1 and 33 batteries in the area 2, the computational times are very, very low. So the 16 milliseconds per iteration and 21 milliseconds per iteration. So we can see that the framework scales very well, and it requires only a low-cost computing unit for each agent. And now I have two slides just to outline quickly the voltage support. I don't know if I have time, Stephen.
Yeah, there's about 18 minutes left of the total talk, but obviously if we want to leave some questions, maybe.
Yeah. That's great. So I will be quick. I have then only 3 slides. Here we also developed another OCO-based control algorithm for voltage support. Here the control objectives are not only to, of course, to keep the voltage at each node of the local distribution network within the limits, but also to track voltage references instructed by the system operator at specific grid supply points. So interconnection points between the transmission and the distribution network. The problem aims at minimizing a cost function associated with each battery unit based on the network parameters. And there are these tuning parameters, these gamma and omega, included to balance the voltage regulation and the storage power provision cost. So they are tuning parameters. And the constraints include the network model, the storage dynamics, and operational constraints, and also the voltage limit on the voltage magnitude at each node of the distribution network. Here there are some simulation results, and we consider an IEEE 123 bus test feeder with 100 residential battery systems and PV generators as well. We see that here we have 3 grid supply point through 3 specific transmission distribution interconnection points where there are the batteries are required to track a time-varying voltage reference instructed by the system operator. We perform a comparative study to demonstrate the improved performance of the proposed approach. So in the bottom figure here, we can see the resulting voltage profiles over 12 hours. That come from a fully decentralized control approach, which is an enhanced method combining 2 traditional approaches: automatic voltage regulation and power factor control. Is a rule-based approach, and our approach, which is depicted in the top right figure. And we can see that while the decentralized approach yields voltage violation, our the voltage profiles at all buses resulting by the application of this distributed approach are kept within the limits. And this here, you can see the load and power, solar power profiles throughout this over these 12 hours. And I also would like to mention that the maximum tracking error is very small, basically less than 0.01, and the computational time to calculate the battery set points, here we have both active and reactive power set points, is very, very short, just 8 milliseconds basically. Now I will skip this, but as I said, I will be happy to share all the slides and discuss with the interested colleagues. And then I would just like to conclude with some practical remarks on this distributed control framework. We started the implementation of them in a laboratory at the University of Zagreb. We collaborated with them within the European crossbow project I mentioned before. And a preliminary experimental results show that when the communication delay is small enough and the agent communication is synchronized, the convergence accuracy is very negligibly impacted by the communication delay. However, if the communication delays are not uniform and more significant, the agents have problems, cannot converge, might not converge to the correct values. And also there is an error in each agent might propagate throughout the multi-agent system and accumulate over time. And the cause of the error might range from communication, not synchronized communication delays to cyber attacks. It has been theoretically proved that the effects of communication delays on distributed algorithms in general can be reduced or even eliminated when the communication delays is bounded, and also when the communication network is efficiently designed. However, there are more studies to be performed to experimentally validate these theoretical findings, and this is of course part of our current studies to of course, extending this control framework to handle additional services, but also to incorporate explicitly uncertainty modeling, including the communication and network communication network related uncertainty. And with this, I will conclude the talk, and I will be very happy to take any questions. Many thanks.
Brilliant. Thank you very much. That was really interesting. And yeah, I'll just repeat that you will be sharing we'll be sharing the slides after so you can see the rest of the material. We've got a few questions in the chat. I'll just ask one myself. I think you alluded to it just at the end about missing data in some ways. So I was interested in the data requirements for the method. You know, how robust are sort of gaps in communications, say, or also maybe gaps in certain local controllers is this, and how, and like what modifications could you do to the method to sort of counteract that, or at least make it more resilient, I guess.
This is a very, very important point, and it is actually the topic of our current research. So it's, I must say that if there are very simple approaches that you can adopt when there are missing data. So you can keep the same control input than the one previously calculated, for example, because the change might not be substantial. And as I said, when it depends on the how large is the gap or how large is the communication delay. The good thing of this framework is the plug and play capability. So the fact that if an agent fails, you do not need to retune or redesign the algorithm, but the algorithm is able to recalculate and redispatch the agents in a very short time. So the failure of 1, 2, 3 agents or more, it does not impact significantly the performance. But as I said, the uncertainty related to the communication issues have to be more extensively and experimentally investigated. So we need to do that. And there are several techniques, approaches that can be thought to make the control framework more robust. And there are stochastic approaches, so basically trying to estimate the probability distribution of the uncertainty, always based on data, and try to sample to incorporate a specific number of samples, and there are theoretical results that tells you how many samples you need. Usually there are a lot of there are many samples that you need, and this is a problem from a computational point of view. Another approach is using machine learning, so trying to use again data to learn about the environment and try to use feedback to counteract the impacts of the environment on the agent performance. And this is something that we have tried to do with the second control framework that I presented, the one about the automatic generation control, the contribution from the batteries. So the feedback and the fact that they're not, because there is also the predictions can help. Definitely. I've been working with model predictive control many years, and there is a improvement of the control performance when you have an idea of what is going to happen in the future. But when you have such strict time requirement, that might not help. So these frameworks do not need prediction and performs quite well because you have a learning and you have a feedback mechanism that can help compensating for uncertainty to some extent.
Okay, thank you very much. Okay, so Andre has a question. Said, hi, Alessandra. The results for the distributed BES control study look great. So that's a nice compliment. Does it mean the problem of de-error control is almost solved? I guess we've already heard that there's one problem, but I guess the question is, what are sort of the main challenges and assumptions to work on? So yeah, what are the big problems?
Yes, I think that the big problem is to test this on a real system, and I'm pretty confident that when we are testing these on a real system, we will encounter several issues, practical issues that needs to be solved. Because on a simulation, with simulations and also on papers, so theoretically, there are guarantees, and this helps. So these guarantees help. But what you can theoretically prove, at least has been proved so far, is the asymptotical guarantee. The guarantee that the constraint violation and convergence to the optimal decisions will happen asymptotically. So there is not any guarantees that in practice the violation and conversion to the optimal decisions will happen, will be achieved within a few seconds. This is what we observed, but there is not any guarantee. The guarantee is about this convergence and the constraint violation going to zero at some point in the future. So that will happen, but we cannot guarantee that that happens under any conditions or in any all the possible systems within a few seconds. Now there are in the literature there are very interesting distributed control approaches that can guarantee a finite time convergence or a fixed time convergence, and we are working on that. But again, it's very complicated problem to derive the mathematical proofs that can guarantee that. And also the other problem is the convexity requirement of these frameworks. So when I haven't presented the other application, which is multi-energy networks, if we want to do that and consider the whole system, so also the other energy network, so the district heating and cooling network, for example, and consider buildings and devices that can provide flexibility, also taking advantage of the interaction between and the different time scales of the different energy vectors. If we want to do that, the non-linearities and the non-convexities are very, very hard, and these frameworks might not be available, might not be suitable. So there are many problems to solve yet. Or Steven,
Sorry, I was on mute, of course. I'll try maybe two very, we've got a few more questions, but maybe two very quick ones. We've only got 3 minutes. But the one I guess from Kevin is asking about balancing really the cost of the energy storage and the fluctuating electricity price. You know, is there some decision making around how you can, you know, determine this solution to use really versus say other solutions? Maybe looked into that costing really.
Oh, here actually one of the advantage is that it's very flexible control design. So as long as you meet some quite mild convexity requirements, you can incorporate in the objective function the electricity price, the costs, all the cost terms that you are interested in. And actually, we have done that. So we included the costs related to the battery operation and the degradation and the reward that is provided by the system operator. You can include time varying electricity price. You can include weighting factors that allow you to achieve the desired trade-off between the different terms. So it's very flexible, and that can be done.
Thank you. So very general approach. So I'll skip yours now, Hid, because I think that was answered at the start. So you'll see that in the recording. So Milad has a question, which I think is quite interesting. One important aspect is to investigate the impacts of such models on the DSO's technical and financial operations while assisting in frequency issues. But the question they ask is, what would be a proper TSO-DSO coordination strategy here? So that's quite interesting.
It's very interesting, and it's not something that we have explored yet. So the DSO, DNO, and TSO coordination. I think that here basically the frameworks for fast frequency and voltage support are for aggregators or distributed network operators. They do not really include the voltage support includes the transmission system operator, because actually we know that the transmission system operators have always had voltage issues at the grid supply points. So that's why we thought of having the transmission system operator providing time varying voltage reference signals that have to be tracked. So there is not any specific coordination between the two network operators to be assumed here. It's just the provision of this reference points. The other framework is mainly for the transmission level, but this is a very important point, and definitely there needs to be a coordination between the different network operators, but not only transmission distribution, but also the network operators of the other energy networks, gas, district heating, cooling networks. If we really want to adopt a whole system approach, they need to exchange data, and they need to agree on some operational strategies. But I don't have an answer yet.
But there's an interesting research project there, maybe.
Absolutely,
so get in touch if there's.
Yes.
Well, thanks for that. So we run a bit over time. But I just want to say thank you very much, Alessandra. It's really interesting. Please get in touch with Alessandra as well through her email. She's very happy to talk further if anyone's interested. I just put in the chat as well the webinar in a couple of weeks from Hussein Kazmi from KU Leuven, who will be giving a talk. So please sign up for the next one. But yeah, once again, thank you very much. We'll be sending the slides around, and we'll put the video up soon. So yeah. Thanks again to everybody, and see you next time.
Thank you very much.
Yes.
Have a nice day. Bye.
Bye.
Bye-bye.